Hey folks, today we're going to talk about the relationship between potential energy, force, and a graph of potential energy. And I'm going to try to relate those to real world examples so you kind of associate the math and the graphing with actual physical situations. So a little review here. We talked about this in the previous video. Force is negative the derivative of potential energy. For now, we'll just stick with the x direction. Um, so we'll talk more about the physical meaning of this in a few moments here, but it, imagine this as a graph. If I gave you potential energy as a function of x on a graph, so some kind of curve, the negative derivative of that would tell you the magnitude of the force, and the plus or minus sign would tell you the direction of the force. Now, we're going to relate this to equilibrium. If a particle is in equilibrium, the net force acting on it is zero. Okay, and most of you are very familiar with this. Now we're going to relate this to potential energy, though. Okay, so turns out there's different kinds of equilibrium. The first kind of equilibrium is called stable equilibrium. And what that means is a small displacement results in a restoring force that accelerates the particle back toward its equilibrium position. Okay, so what does that mean? Okay, so what that means is if, for instance, let's say you have a spring, okay, and here's a spring, and it's up against the wall. Let's say this is the equilibrium position, okay. If I pull the spring right, the force that it exerts is left, trying to bring it back to equilibrium. And also, if I push it to the left, well, now the force of the spring is to the right, trying to get it back to equilibrium. So that's an example of stable equilibrium. Another one is, let's say you have a book on a tabletop. If I lift one end of the book a little bit, okay, then the book tries to go back down to the ground. Okay, so that's what we call stable equilibrium. If I lift it up, there's a downward force acting on it, trying to move it back to its equilibrium position. Now, on this graph here, let's say this is a graph of stable equilibrium. There's a bottom. This is the point of stable equilibrium. One way to look at this is to pretend the graph is an actual shape. In this case, it looks kind of like a bowl. And imagine you have a ball rolling around in that bowl. Okay, well, if you have a ball rolling around that bowl, if you put it where the X is, the ball wants to stay there. And if you move the ball left or right of that position, the ball will roll back to that X. That's stable equilibrium. So for instance, let's say I move the ball to this point right here. Okay. So what's going on there? Well, I've moved the ball to the right. The slope of that graph is positive. The force is negative the slope of that graph. So the force is negative. That means it's in the negative x direction. That means there's a force to the left. A leftward force would try to bring that ball back toward the x. Similar thing over here. If the ball is to the left of the x, the slope of that line is negative, which means the force is positive, which means the force is to the right, which tries to bring the ball back toward that x. Okay. Now, another example of this, or another type of equilibrium, is called unstable equilibrium. That's where a small displacement results in a force that accelerates the particle away from its equilibrium. And I wrote an example there, upside down cone, but I'll do another one. If you have a pencil that the lead is a little flat on, like so, okay, theoretically you can balance that pencil on its tip, okay? And if I give it even a little shove to the right, it'll accelerate away from equilibrium. And if I give it a little shove to the left, it'll accelerate from equilibrium. So that's an example of unstable equilibrium. The thing wants to tip over, wants to go away from equilibrium. Now, another example of that is, imagine this would be a graph of unstable equilibrium. The point of unstable equilibrium would be the very top of that curve. Again, you can pretend the graph is actually like a contour, and we have a ball rolling around on this contour. So if I put a ball right at the top here, it will not move. But if I shove it a little bit to the right, so where it is in the picture right now, then there's a force acting on it. Now the slope of that line is negative, therefore the force is positive, so the force would be away from equilibrium and the ball would accelerate away from our x. And same thing over here. We have a positive slope, which would be a negative force, which would be a force to the left, accelerating that ball away from the equilibrium position. The third type of equilibrium is called neutral equilibrium. That's where a small displacement results in a zero force. So the particle is again at equilibrium. So basically, anything rolling along on a level floor would be a good example of neutral equilibrium. So this ball, it's not, if I let it go, it's not going to accelerate left or right. If it's moving left, it'll continue moving left at a constant velocity. It's not going to speed up or slow down anyway. So that's an example of neutral equilibrium. So we have stable, unstable, and neutral equilibrium. Now, you can often have a graph, and here we got some numbers for you, and they're going to ask about types of things on the graph. So for instance, ID equilibrium position. So that's basically anywhere the graph is horizontal. So here, about there, and then anywhere after 16 seconds. So if I were to write this out, x would be about 0 is the first one, maybe about 3.5 for that second one. The next one would probably be maybe about 9.5 or so. And then the final one would be 16 and beyond. So greater than or equal to 16. Okay, so those are points of equilibrium. Now, they also ask, we should probably write down what types of equilibrium they are. So here we're at a dip, so that's stable. So at 0, we have stable. At the 3.5 second mark, we're at a little peak. If I have a ball up there, it doesn't want to stay there, so we're going to call that unstable. The 9.5 meter mark would be stable again. That's the bottom of a loop. And 16 and after, that would be neutral equilibrium. The ball is rolling around there, then there's no worries about it. It's not going to change its energy. The particle will be bound if its total energy is in what range? So here's a way to think of that question. What's the min and max energy the particle has to have and stay on this graph? Or you can think of it this way. Imagine you have a ball rolling around back and forth on this graph. What's the range of energy that the ball has to have to stay on this graph so it doesn't roll away on us, okay? Well, if I give the ball more energy than right here, which is 10 joules, the ball could roll away. So like, let's say the ball's here and it's rolling left, and it rolls left. It gets to, let's say I gave it 12 joules, just for instance. It gets to 12, it would stop there, but then it would roll back, and when it got to here, it still has some energy left, because it's got 12 joules of energy and only 10 of that's potential, so that means 2 of it's kinetic, and it would roll away and never come back. So the max energy that the thing can have is 10 joules. If it has any more than that, it's going to roll away. Now there is a minimum on here. The lowest potential energy it can have occurs right about there, which is about 1.5 or so. Okay, so our potential energy must be between these two values if it is bound, if it has to stay on this graph. Now, if the particle has 8 joules of total energy, that doesn't say potential energy, that says total energy, where can it be found? Okay, well, it can be found anywhere at or below where it has 8 joules of potential energy. So it can be found between x equals -4 all the way to x equals, that's about 13.5. So I would say from -4 to about 13.5 meters. Okay. Now you can put less than or equal to for these. That's fine. We're looking for a rough range. At x equals 2, what is kinetic energy? Well, remember the total mechanical energy equals the kinetic energy plus the potential. Well, I've given you the total. It's 8. That's the 8 joules here. We can also, off the graph, tell how much potential energy it has. At x equals 2, which is right about there, it has roughly 6 joules of potential energy. So I know that this number here is 6. So what does the kinetic energy have to be? Well, it's got to be 2, okay? So it has to have 2 joules of potential energy there so that the total adds up to 8. Also, the final question is, what is its max kinetic energy and where is this? Well, if something is rolling up and down hills, it's going to have the most kinetic energy where its potential energy is the least. Where does that occur? Well, for our graph, that occurs right there. That's the lowest that the graph gets. So again, I know the total energy is 8. I'm trying to find the kinetic energy. The potential energy at that spot, we said, is about 1.5 if I read off the graph there. So that's about 1.5. So the most kinetic energy this thing could have would be 6.5 joules of kinetic energy now. And where is that occurring? That's occurring at about 9.5 meter mark or so. So we could say at 9.5 meters. Okay. So again, one thing I think that helps on these graphs is imagine it's a ball rolling back and forth along this graph. And you can imagine it has potential and kinetic energy, and this graph is telling you the potential energy of the ball at different heights. So I hope that video was helpful, and I will see you in the next unit.